Hi everyone, my name is Jakub, and today I would like to share with you a few things that I have learned when developing a real-time personalization platform for 30 million of users. And most of those things probably I wouldn't learn if this project was at smaller scale. I'm here on behalf of DreamLab, the IT hub of Ringier Axel Springer. And if you don't know any of those two companies, I'm pretty sure that you know sites like Onet, Newsweek, Forbes, Business Insider. What all of them have in common is that they were created using a platform that DreamLab is developing. This platform is called Ring Publishing, and it provides everything you need to create your own media site. The scale we operate at is that we have around 8 million of articles in total, and with each month we get 200,000 new ones. Our solution is used by 800 editors concurrently, and the content we provide is read by 30 million of real active users monthly. And behind all of this, we process around 40,000 of events per second with everything that is going on the user side. And with each day, we get a new 3.5 terabyte of data. And that's all from over 60 sites in Europe and Africa. Part of this Ring Publishing is the product that my platform was developing. It's called Aureus. It's a personalized recommendation system. It currently processes around 10,000 requests per second. 95% of the requests are responded in less than 20 milliseconds. We personalize content for 30 million of users. We have near 5 nines of availability. And what I think is the most impressive is that we went from 0 to serving production traffic in just 4 months by a team of 5 people, aided by 2 data scientists, and we had a lot of challenges along the way. So let's cut to the chase, and let's talk about the first thing, about how we have chased low latency and high availability. Of course, everybody needs that. Every system, distributed system, needs those things. But let's just go through some examples of why we needed them. What people don't like is when they come to your news site and they get blank page, some error, anything that isn't the news that they want to read. And it can happen due to many reasons. Maybe some exception was not handled properly. Maybe there was sudden spike of traffic that the application did not withstand. Or maybe this guy that we probably all know ran the shutdown command on production instead of his local machine. And because of all of this, we are not able to serve content to the users. That's why we need high availability, and it means to have always more instances than you need, some load balancing between them, just so that you are safe from those situations. And as all of you probably know, there is only one thing that is worse than having no internet connection. It's slow internet, and that's exactly how it is with our need of latency. Because if users come to your page every day for a week, and one time they get an error or this blank page, they will go to your competition, but they will come back, they will forgive you because everyone can have some downtime. But if they come to your page every day for a week, and every time it takes your page 20 seconds to load the content, they are never coming back. They are going away to your competition, and you have given up a customer without even putting up a fight. And what is the easiest yet most effective way of reducing latency in some distributed systems? Some distributed system which may do some heavy computations, has some slow databases that it uses. You introduce caching, and everything is great because the request bounce off the cache, and you can return content to the user in milliseconds instead of seconds. Well, at least as long as the entry in cache is valid, because the moment that it expires, all those 10,000 of requests go downstream to all of your fragile dependencies, like those slow databases, and those are probably just like people. When they are doing something very important and they need to do it as soon as possible, it doesn't help if 10,000 people come and ask them for the very same thing. Of course, solution to this is quite simple. You have to block all the requests except one that you let through, and the rest wait for the single request to finish. After it finishes, the cache is updated with new entry, and we can return content to the user. That's great, but these heavy computations, so database lookup may take even 15, 20 seconds, so we have just lost our low latency. And what is the solution to this? We introduce stale caches. If you don't know what are stale caches, it's when an entry in cache expires and someone makes a lookup for this entry. You return the previous value associated with it, even though it may no longer be as accurate as possible. It is still better than waiting those 50 seconds, and you trigger an asynchronous refresh in the background to make sure that you will have, after some time, the up-to-date info. And it goes exactly like this, that when those requests come to the cache, they return the stale value associated with the key, and some refresh is triggered. It may take like 15, 20 seconds, but we don't care about this because we have returned in milliseconds and content to the user. And this is finally the cache that we are happy with, because when the application starts up, the first few requests might take a little while longer, but all the rest will bounce off the cache. Some of those requests will trigger an asynchronous refresh, and everything should work okay. And so we thought, until one day the business owner comes to us with their laptop and says that every now and then when they come to their page, they see news from an hour ago, from 2 hours ago, sometimes from yesterday. And it cannot work like this because publishing is time sensitive. They write 7,000 articles each day. When some breaking news happens, we need to show it as soon as possible, because otherwise we are losing customers, because they want to read about those breaking news. They want to read new articles, not some news from yesterday. So we took a look at the laptop of this business owner, and let's imagine that this Wikipedia page is published by our system. As we can clearly see, Pluto is 9th and smallest of the traditional planets. Wait a second. It's no longer true, it's old news. Of course, you remember that you have this stale cache in your system, so you just press F5 and you have up-to-date data. And it's great, but just to have clear conscience, you want to show the business owner that everything works fine. You press F5 and all data once again. How is this possible? Well, do you remember how we have talked about the high availability? It means that we have more than one instance. We have some load balancing between them. And some of you probably might already know where this is going if we combined it with stale caches. But let's go with the request flow so that we are all on the same page. We have this whole bunch of traffic coming to cache key calculator, which, as you can probably guess, calculates cache key for some versions of homepage. And those versions, to give you an example, may be like a site with more sports news, and it may be our version A, while version B may be like more travel, might be more news about travel and stuff like this. And we retrieve data from cache every now and then, let's say every minute for simplicity. We trigger a asynchronous refresh, which goes down to our recommendation system. Of course, it is a distributed system, and it means that it has some instances of its main API. It has, each of those instances has its own in-memory cache, and they connect to some heavy computations, so databases and other resources. So how does our request go through the system? It goes to one of the instances, which handles it, retrieves data from cache, and returns the data to this big cache, where it will be from where it will be returned to the users. Well, there's just one problem. This in-memory cache also might have a stale value, so this value is old, and only after this request is returned, we have up-to-date data in this instance, but not in 2 other instances. So in perfect world, in this scenario, every third request that we process would go to each of the instances, and we would have 3 minutes old data in all of them, which is not that bad, but could be better. But we do not live in perfect world, and we do not have any guarantee that the traffic will be distributed evenly. It is because if you have this one request for one version every minute, it is pretty slow traffic, and load balancers are never guaranteed to distribute it evenly. So let's imagine that we have 5 requests over 5 minutes, and we have 5 instances. This is perfectly normal way the traffic will distribute. And if we combine this traffic distribution with dozens of instances, then you know where the one-day-long news came from. Now that we know all of this, I think that pretty logical conclusion would be that it's all because of in-memory caches in our instances. Because if you get rid of them, those instances are behind a cache. So it doesn't matter if they respond in 15 seconds or 20 milliseconds, right? Well, that's true as long as this cache lives, because the moment it breaks, that there is higher traffic coming to our main APIs, and each of those instances makes, with each request make synchronous call to all of its dependencies, and they will not like it and will probably die. So that's why we need those in-memory caches, because even if the big cache breaks, we still can save all the dependencies. Okay, now that we know what is the problem, let's focus on what we need to do. We need to have a low latency and up-to-date data. Some of you might think that this is a little bit impossible because of this thing called PAC-ELC theorem, which is mathematically proven that it states following, that if you have network partitions in your system, so some of the nodes may not communicate with each other, your system will have to either prefer availability, so it will return the data, even if it's not up to date, or it will be return consistent data, or don't return any data at all. So it does not have guarantee that its data is up to date, it does not return the data. And this half of this theorem is derived from the CAP theorem, and we are more interested in the second half, which states else. So if the system is working normally, there are no network partitions, you have to choose either latency or consistency. And it contradicts our requirement of having low latency and up-to-date data. And it's mathematically proven. But of course, we are engineers. We can make some trade-offs. And in our case, it was to assume that the data is consistent enough if it is up to 1 minute old. And if we make this assumption and focus all the way on the latency, then we can every minute just refresh all the time-sensitive data in our caches, and that's what we did. We scheduled a job which every minute refreshed all the entries that were time-sensitive, and we finally had working solution. There were no longer some yesterday's news, and everything worked great with just some minor bump along the road, because one day we have changed the way cache calculator works. It started taking into account some new variables, and because of this, versions A and B became versions C and D. And what did our cache refresher do? It kept refreshing A and B and C and D, even though the first two were no longer in use. How did we deal with it? By introducing a custom solution, which checked when the entry was originally added, when was it last accessed, and based on it, it determined whether or not it should refresh this entry. And that's how we have finally added caches to our application. And as you can see, it was not that easy, But as we all know, caching is one of the two most difficult problems in computer science, right next to naming things, so it has to be serious. So let's talk about something simpler, like scaling. I'm not even talking about auto-scaling, I'm just talking about having more instances than one, some load balancing between those instances. And imagine that your load balancer has this great new feature where if an instance doesn't respond in time, it can still forward this call to other instance. And it's a great solution which increases availability of your system. Because if the application dies during request processing, user can still get the data from another instance. And what can possibly go wrong, right? Let's see. We have this load balancer which distributes traffic, and suddenly some spike of traffic came, and each of the instances starts processing more requests. If they start processing more requests, it means that they create more objects, they spend more times on garbage collection each minute, and the probability of those requests timing out increases. And let's say that some of the instances start to time out. Load balancer in this scenario forwards those requests to other instances. Please note that the input traffic remained the same, while the traffic inside the system has suddenly started multiplying. And of course, it goes on again. New instances start working even slower because they have even more traffic. And load balancer redirects and goes again and again until even some instances come up. They get so much traffic into them that they die on the spot. And in our case, it was because of too many open files exception. It means that we have run out of file descriptors because of the number of open connections we had. And because of our infrastructure, we couldn't simply increase the number of descriptors available, so we had to go around this, and we have created some well-designed solution, which in case of traffic was supposed to monitor number of open connections. Then if some threshold was exceeded, we started queuing them up. If queue finally filled up, then we started returning some HTTP error, which meant exactly that this scenario happened, and we could easily distinguish it in some metrics, maybe put some alarms on it. But what happened was almost the same. I mean that we started monitoring connections, queues started to fill up, we started returning these HTTP errors, then everything died because of too many open files. It turns out that this solution was not very efficient. And by not very efficient, I mean that this queuing up and returning HTTP code took like a millisecond. And in this millisecond, there was so much traffic incoming because of this multiplication I told you about, that in the fraction of a second, all the open connections were finished. So we had to go for something easier, a little bit uglier, but working. We were still monitoring number of connections, and if some threshold was exceeded, we raised a flag and started rejecting all the connections. And the result of this rejection was that we even didn't accept the connection, just connection refused error, which made it difficult to distinguish this situation from any other, which might result in connection refused. But it was something that we have to live with because our instances don't die anymore. So as you can see, load balancing and scaling is not that easy as well, especially if there is some new great feature that you didn't test before putting it to production. And let's talk about data processing. As I have told you, we have created a real-time personalization platform, and it means that we didn't go for batch processing. What is batch processing? What is batch processing? It's when you periodically make some computations, like every 15 minutes, every hour, every day, and you calculate the result which you use until the next computation is finished. Just like this dog over here, once it gets its water bowl full of water, it will drink from it until its owner comes back from work and will refill it. So why didn't we go for this solution? Even though offline processing is very accurate and relatively cheap, it has one big disadvantage, the latency it introduces. Because every 15 minutes, we would be, in case of recommendation system, we'll be taking a bet, whether or not the content we provide will be interesting to the users, or maybe they will not like them. And also, we have very limited ability to return some, to post some breaking news which happen, and we need to give information about them right away, because we have job running every 15 minutes. So because of all of this, if the people don't like the content, they don't see some breaking news when they come to the page, we are all losing money. And that's what the business does not like. So we went for real-time processing. And there are many tools to choose from in case of real-time processing. And we were supposed to choose one. The easy choice was Apache Storm, because it was used for many years in our company. It is a well-established solution, which is a good performer, but unfortunately it has a low-level API, which makes it kind of cumbersome to use. So we wanted to try out some new solutions, some new technologies, and just to make sure, it happened around 2016, 2017, when we were reevaluating them, so the reasons why we didn't choose them are no longer accurate. In case one of the tools was Apache Spark, which has high-level API, but it has batch-first approach. So it is not made for stream processing by default, by design. And back in 2017, it had to emulate streaming using micro-batching, which introduced some latency that we could not tolerate. Of course, as I have told, it's no longer true with Apache Spark version 2.3. There has been introduced continuous mode, which fixes it, but we didn't know about this then. So we had to reject Apache Spark and went for Flink. Flink also has high-level API. It is stream first, just like Storm, so no need to micro-batch. It has better performance than Storm. But back in 2017, it was not mature enough. And we simply could not do all the things that we wanted to using its API. And those two technologies, Spark and Flink, were really hyped back then. But when we tried them, all we found was a brutalization that they are not as good as people tell, that they are not as good as people tell they are. And it's all according to Gartner's hype cycle, which states that when a technology is everywhere, it might not be as good as everybody thinks it is, and only after some time it might be good enough. In our case, it was with Flink because we have evaluated it a few months ago, and we have finally decided that it meets all of our requirements, and we have decided to add it to our technology stack. Of course, it does not mean that if there is something, the technology is at this peak of inflated expectations, you cannot use it. Even we probably would have used Spark streaming if we were operating at slightly slower scale, and this micro-batching would not be that unacceptable. Or maybe we wouldn't have so many complicated use cases that we couldn't solve them with Flink. Okay, last but not least, let's talk about the personalization. When we are given business requirement of the personalization platform, we are asked to do one-on-one approach. And it was around a year and a half ago when every company like Netflix, Amazon, LinkedIn was telling that they did one-on-one personalization, they had so much success with this. So we are happy that we can learn from their successful cases. So we sat down and analyzed this scenario. And let's go with how the most popular algorithm for one-on-one personalization works. It is collaborative filtering, which tries to find the most similar user to the one you are trying to figure out something about. So let's say that we want to know whether or not user 5 will like the film number 3. So we want to find the user that is the most similar to the user 5. Of course, it is user 2 because they like the same films. And because the user 2 does not like film 3, we can assume that user 5 will not like it as well. So that's the basics of how collaborative filtering works. So let's see why we couldn't use it. Our data is a little bit too complicated, too dynamic. In case of Amazon or Netflix, their products, films have a long lifespan, while our articles while nobody reads our articles after maybe a day, maybe a 2. So it would be very difficult to have a lot of historic data. Also, we create 7,000 new articles daily, and the people read around, on average, 7 or 8 of those articles. So this matrix would be pretty difficult to create. Not impossible, but difficult. Also, we don't know anything about 25% of users that come to our system each day. And one-on-one approach also means that we have to disable all the caches, and costs go up a lot. So we decided not to go for one-on-one approach, just for the right solution, which is a little bit simpler, but first of all, it is what we should do. Instead of one-on-one, we divided people into some segments. Let's say some evergreen segmentation at the very beginning, like people interested in sports, in travel, and in celebrities. And for each of those groups, we have run a simple real-time algorithm. We didn't choose them because they were easy to implement, but because we have compared the maintenance cost and the profits that they will bring with complex solutions like neural networks. And to this day, I'm very amazed at how well the simple algorithms perform. In case of being effective, they outperform neural networks a few times in our use case. And you know what? Even though we didn't do what the business asked us to do, everybody is happy. Users are happy, the business is happy. How do we know this? Because of the results. Our users make, on average, 12% more visits each month. We have 7% more active users than before personalizing. Our click-through ratio raised by 43%, and it means that people started reading more articles when they came to the page the same amount of time. And they started spending over half more time on our site. And I think that is pretty clear example that the users are happy. And why is the business happy? Because behind all of this, there is money. And it's all because we have decided to first make a working solution and then make it better. And that's actually it from me. Here are some key takeaways from this presentation. First of all, remember that caching and scaling is a must, but it is also difficult, and you should be always very cautious when you approach this subject. Secondly, you can't always get a nice solution. Thirdly, never go blindly after the hype, and make sure that you use the best suited tools, even if they are not the trendy ones. And finally, first make it work, then make it better. And if you have found any of the challenges I have described you interesting, or would like to be part of this of the team that creates this personalization platform, where we work close to the business and we are focused on solving the business use cases, please apply. And that's it. If you want to have any questions, you can ask me here or approach me after the talk or send me an info or if you have any feedback. Thank you.